Excellent. I will say I'm in charge at the university of our total research portfolio, not of doing the IT and lecture theatres. You can see why. So good evening, everybody, and thank you particularly for those people who braved the rather fractious Leeds weather to appear in person tonight. What I want to do over the space of the next 40 minutes, 45 minutes or so, is take you through a journey around why toxicology is important. And I'll touch on many different aspects that I've had to look at over my career, and hopefully make you think a little bit about how you would respond in those sorts of situations. So as an idea of what we're going to talk about, we will start off by, I'll tell you a little bit about what risk is, and I will think about risk from a scientific perspective. Then I will go on to say, okay, well, now we know what risk is. How do we actually use it to increase safety? You'll notice that I don't say ensure safety. We increase safety as much as possible. And I'll spend time talking through endocrine disrupting chemicals as a case study and a way of thinking through the process that we go to ensure that every single one of you in your everyday lives is as safe as reasonably practicable. And then I will try and bring it all together. So this is where I get to judge the age of my audience. Those of you who are slightly on the more mature side will undoubtedly remember the Marlboro Man. The Marlboro Man is an absolute wonder of advertising. So if I take you back, everybody, men smoked roll-ups. That's what you did. The problem is cigarette companies realized there wasn't much money in rolled cigarettes. It was very difficult to corner the market. It was difficult to make a profit. They really struggled to make money. Where the money was in filtered cigarettes. The problem is only ladies smoked filtered cigarettes. And most of the money was made through men. So what did Marlboro do? They created the Marlboro Man. This was the ultimate rugged cowboy. You may well remember the adverts. He rode on his horse across the plains in America. He was the cowboy. He was the epitome of manliness. And if you read in the advert, it talks about this being the full-flavored, manly scent. This was how you felt like a man. And it worked. This campaign absolutely transformed how people smoked. And people switched almost completely to filter-tipped cigarettes. So what's this got to do with risk? Well, there were 7 Marlboro Men through the advertising campaign. Every single one of them died of smoking-related disease. I'm quite anti-smoking, you might tell that. Let me introduce you to somebody else, Antonio do Campo Garcia. Antonio is fantastic. He died at the ripe old age of 107. By his own admission, he would happily drink 4 bottles of wine for lunch. Him and his son went through 200 litres of wine a month by their own recollection. But he lived to 107. So basically, don't smoke, but have a nice glass of red wine. This fits with my personal philosophy. But is that how we should do risk assessment? Should we look for the answer that we want? I don't want to smoke. I do want to drink red wine. This fits with my narrative. This is confirmation bias. Do we really want to base the safety of everybody on one individual or 7 individuals? And this is where I introduce my third person, Roger Brinner. So Roger Brinner was an economist. He's had several jobs, from being a chief senior economist at the White House through to working to consultancies like McKinsey. And he said, the plural of anecdote is not data. And This is really important. We spend our lives talking to people. We spend our lives listening to the news, watching social media, picking up little bits of information. And the problem is, we often try and package these together to come up with a conclusion, and a conclusion that fits our viewpoint. That might be okay if you're trying to decide who you want to win Bake Off. It's not okay if you're trying to decide whether you should regulate a drug or a chemical from exposure to humans. We have to think in a more robust way. We have to really test the limits. And this is what I want to talk about as we go through this talk. So to do that, I need to tell you a little bit about how we start to use risk to increase safety. So I need to think about how we calculate risk, how we manage risk once we know about it, and how do we talk about risk. And when risk people get together, we really think about three things. So we think about risk assessment. This is what I've done for most of my career. I have taken large amounts of data, looked at them, and come to a conclusion based upon the data that says, this is the risk to this particular group from this exposure to this chemical. That's really useful. It means I've had some really strange meetings. I suspect I am the only person in this room who has calculated the level of chemical exposure from a crock into a 6-year-old Danish child's foot. But we've done that to make sure that you are safe if you ever wish to wear Crocs. Once you've done the risk assessment, the next question is, how do we manage that risk? So there are some risks I'm going to show you where actually, for all intents and purposes, we can ignore them. They are such small risks that you really shouldn't worry about them. There are others that I'll talk about where we have to take action to protect either human health or our environment. And that's where risk communication comes in. Risk communication is how we talk about risk to the wider public. How once we've decided what we need to do to manage that risk, we try and communicate it out. As a scientist, I will put my hand up and go, we're usually really bad at communicating. We usually lose an audience within the first 5 minutes. And that's a problem, because as I show you, that leads to the challenge of risk perception. People come to their own conclusions and get overly concerned about things that they really shouldn't worry about, and perhaps don't worry about the things that they should. So to try and talk this through and make you think about how you should use risk within your lives, I'm going to pick on a particular group of chemicals called the endocrine disrupting chemicals. Now, I suspect you may never have heard of EDCs before, but I bet by the time I get to the end of this slide, you will have done, and it will remind you. So I'm going to go and pick through just a few examples of what endocrine disrupting chemicals are, and then I'll go on to tell you what they do. So you may have seen in the news recently the threat of what they call forever chemicals. Things that are in our soil, they're in your bodies, they will be here forever because they break down so slowly. And then the question is, what are they doing while they're in your soil or in your body? PFAS, these are classical forever chemicals, and they are part of this group of chemicals called the endocrine disrupting chemicals. If you're a little bit older, you may remember the dioxins. The dioxins were the original forever chemicals. Dioxins were banned from use in most parts of the world in 1971, the year I was born. If you measured my blood I guarantee there would be low trace content of dioxins in it, because it's so persistent. Even though it's been banned for 50+ years, there is still dioxins circulating through humans, animals, and plants. So again, dioxins actually are endocrine disruptors. But what makes endocrine disrupting chemicals so prevalent is they are used in a wide range of different processes. So you find them in flame retardants. The fire extinguisher over there, that will contain endocrine disrupting chemicals. Fire blankets contain endocrine disrupting chemicals. You're exposed to them. Phthalates, I will come back to phthalates. They are plasticizers. They make plastic bottles into the shape you want, and many other things. Pesticides, many pesticides are endocrine disruptors. If it gets sprayed onto a field, then if the field, it may end up in the soil, it might run off into the fields, we'll talk about that, and into watercourses. It may stay on the fruit and vegetables that you then ingest, so you're exposed to them. Bisphenol A, we'll talk a lot about this. Bisphenol A is again a plasticizer and probably the most famous endocrine disruptor. But finally, I wanted to pick this group here, phytoestrogens. These are natural products. Phytoestrogens are made by plants. They are endocrine disrupting chemicals because plants have a war going on. And that war is against predators, things that will kill it. So if a man-eating tiger ran into this room now, then our survival strategy would be simple: run away. A plant can't do that, it's stuck. It cannot escape the things that will damage it, whether that be mold, whether that be bacteria, whether that be a cow. It cannot run away. So they develop their own chemical defense mechanisms. Phytoestrogens are part of that. Phytoestrogens form very powerful antifungal agents that protect plants. There's actually examples where, under very specific conditions, you see a reduction in the fertility of birds that eat specific plants that contain lots of phytoestrogens. So we know these natural products can change how animals reproduce. So endocrine disrupting chemicals are everywhere. And when I say everywhere, I mean everywhere. You cannot possibly read everything on here. This is a study that was done a few years ago now, looking at all of the endocrine disrupting chemicals. There's about 700 of them and what they're used for. The size of the box tells you how many chemicals are involved. So pesticides are the biggest group of endocrine disrupting chemicals, but they're in drugs and pharmaceuticals, they're in healthcare products, they're in food additives, household supplies, environmental pollutants, stationery, lubricants, solvents, fungicides. Pretty much anything you're exposed to probably has an endocrine disruptor in it at some point. You cannot escape exposure to these chemicals. So what do they do? Why am I, as a toxicologist, concerned? Well, to do that, I think I probably need to take a step back and tell you what the endocrine system is. I've told you these chemicals disrupt it, but if you don't know what it is, that doesn't tell you anything. So when you think about how animals communicate and organize the trillions of cells within their bodies, they do this by sending signals between different parts of their bodies to help them work. And these are basically split into the paracrine, endocrine, and exocrine systems. Paracrine is one cell talking to another. So it's really short distances, but it's where a cell, for example, is stimulated by something and starts to respond. And it will send a signal to the next cell going, look what's just happened to me. You should probably get ready for that stimulus as well. So it gets that local response going. Exocrine is at the other scale. It's outside of the body. So it's your body releasing tears or sweat or breast milk. So it's things that come out of the body that help or other parts like your skin, your eyeballs function and work correctly. The endocrine system, which is the one that I'm interested in, is the within-body signaling system. And it effectively allows your brain to talk to other organs within the body. So a classic system is the so-called HPA, hypothalamic pituitary adrenal axis, which your hypothalamus is a small part of your brain. Your pituitary sits up here, and then your adrenal glands sit on top of your kidneys. This is what would be activated when that man-eating tiger comes in, because your brain sees the tiger, sets off a signal that releases a chemical that causes two things to happen. First of all, adrenaline kicks in, makes you awake and ready to react. And then secondly, glucose is released from your liver to give you the energy to run away and keep on running. That's your fight or flight response. Now, if we start to disrupt that or overstimulate it, we know bad things can happen. So as an example, we know that soldiers who spend a lot of time in theatre, so a lot of time being deployed, being stressed constantly because they're in risk of their lives, actually when they finish working, they are more at risk of diabetes, cardiovascular disease, because they've constantly been firing off this system. And this system sends lots of glucose into your bloodstream and can actually lead to insulin resistance, the first step through to diabetes and so on. So we know that overstimulating these systems can cause a problem. So that's the theory. I said I wanted to talk about risk perception. To talk about risk perception, I have to go to my favorite publication for scientific knowledge, which is the Daily Mail. The Daily Mail is a wonderful and august journal, but all newspapers are there to sell copy. And you do not sell copies by going, everything is lovely. You sell copies by having stories that people want to read. So they're either really sort of interesting and juicy, or they scare people. So I did a very quick search of Mail Online to see what it told me about endocrine disrupting chemicals. This is the articles that were published over the space of about 2 years. So apparently they're in dolphins' urine. And if they're in dolphins' urine, it's due to the fact there's so much plastic waste in the sea. So we're not just exposing ourselves, we're exposing marine wildlife. They are gender-bending chemicals found in plastic and linked to breast and prostate cancer, and they're found in 86% of teenagers. Pregnant women, you should never drink from plastic bottles. They contain hormone-disrupting toxins that will make your baby obese. Would you give up makeup to guard against breast cancer? Chemicals in shampoo, toys, and floorboards may risk the risk of obesity. Pregnant women who wear perfume and use plastic containers may have problems with children.
It's on the right.
Time to go organic. Gender-bending chemicals in cereals now could also make you fat. And there are finally 12 everyday items that are wrecking your hormones.
Carriage straight on. It's on the right.
Whether that comes from tooth fillers, to toothpaste, to shopping receipts. So in the space of about 2 years, pretty much everything is out there to kill you. That's risk perception. So let me unpack that a little bit and go, should you genuinely be worried? Is this real or is this not? So to do that, I'm going to give you 2 quick examples. And my first one actually comes from my PhD. As Rachel very kindly introduced me, my PhD was in an area of toxicology around liver cancer. And at that time, there was a scare story, funnily enough, it was from the Daily Mail, around wrapping soft meat, soft cheese, sandwiches in cling film. Because the chemical that makes cling film clingy is an endocrine disruptor. And the theory goes, if I wrap my cheese in cling film, the endocrine disrupting chemical will leach from the cling film into the cheese, then I will eat the cheese, then I am eating the chemical. And we know that on the right-hand side here, you can see what happens if I give that same chemical to a mouse. So the first thing that happens is this shows you the weight of a mouse liver. And as you give it more of that chemical, the mouse's liver gets bigger. And it does that, not just the whole animal gets bigger. Actually, when you compare it to body weight, it gets bigger. The liver is getting larger compared to the rest of the animal. If you look within that liver, what you see is these are sections of the liver. On the top is just a stain, so you can see in the red is the cytoplasm, and in the blue are the nuclei. And at the bottom, what we have here is a stain that
And then turn right,
and
and it's on there.
You're looking for
You
red
turn
dots.
right, and it's on there.
What you can see is, as you increase the dose of this chemical, first of all, you go from a beautiful looking liver slice. Trust me, I'm a toxicologist. It's a beautiful looking liver slice, through to one with lots of holes in it. But they're not actually holes, because if you look at the stain below, you can see lots of little red dots. This is fat. And what's happened, as you give more of this chemical, the liver is making and storing more and more fat. And that's how you end up with a fatty liver. If you continue to do this, you drive the liver down a pipeline that goes from fatty liver to liver damage, to liver failure, or liver cancer. And if I give this chemical to rats or mice, about 70 to 80% of them will get liver cancer and die. Why on earth is it in cling film? So my first job as a PhD student, my boss made me go away and look at the risk to humans for cling film. So I sat down with a piece of paper and a pen and calculated roughly how much cling film would equate to the same level of dose as these mice were receiving. So how could I achieve the same level that was killing mice in a human? And the answer is you can, but to do it, you would have to eat 7 rolls of cling film every day for the rest of your lives. Now, if you're doing that, you probably have more problems to worry about than getting cancer in 20 odd years' time. So, is it a risk I should be concerned about? Probably not. There are bigger things to worry about. So we noted, and I still wrap my food in cling film. I'm perfectly comfortable with it. You will see that there is some advice that you shouldn't put things in cling film and then heat them in the microwave. I will come back to why you shouldn't do that in a moment. But generally, it's perfectly safe. So that one I've pretty much myth busted. What about this one? So back in the late 90s, early 2000s, we were starting to get quite a lot of reports about feminization of fish in rivers and in lakes. The first reports really came from the Great Lakes in America with smallmouth bass. But what I'm showing you here is roach in British rivers and canals, because we're in Britain, we're not in America. And this is real. So if you look at the figure on the right-hand side, what you can see is high risk, medium risk, and low risk is the chance that there is actually an endocrine disrupting chemical in that water, how polluted the water is. Where we have highly polluted water, up to a third of the male fish have symptoms of being female, whether that's testes developing eggs or actually the males developing their own oviducts. So these are male fish with female characteristics. This is real, this is undeniable. This is an animal living in the wild that has had its whole physiology changed by exposure to endocrine disrupting chemicals. So the first question is, which chemical is it? We don't quite know, because all endocrine disrupting chemicals have this potential. It may well actually just be estrogen from the female contraceptive.
I knew that.
Flushed down the toilet and then going out into rivers as untreated waste. But it may also be things like bisphenol A that I'll come back to. So there are lots of opportunities where you could have that exposure.
So
I'll see if I can. It's only one individual, so I'll just, yes. So this is an example where this is a genuine risk. And if this is happening to fish, why is this not potentially happening to us if we're exposed to endocrine disrupting chemicals at the same level? How do we stop this? Well, we can stop the fish by not releasing untreated sewage into rivers. We can also worry about runoff from agricultural fields that might put endocrine disrupting chemicals into the rivers. We can reduce that exposure, but it's not going to 100% go away. So actually, I should worry a little bit about EDCs. So is there a risk to human health from endocrine disruptors? Theoretically, yes. They have what is known as a hazard. They could be hazardous to your health. The question is, how do we minimize that risk? I cannot remove it unless I block all of those chemicals. But how do I block it as much as possible? So here, what I'm going to do is I'm going to tell you a little bit about bisphenol A. So bisphenol A is probably the most famous endocrine disrupting chemical. It's used as a plasticizer. Pretty much anything you use in your life that is made from a plastic chemical, from plastic, has an endocrine disrupting chemical in it. Whether that be, I don't seem to be able to mute him permanently. Whether that be a bottle of water that you're drinking over there, it has a plasticizer to form it. Whether it be this phone case, it will have a plasticizer that's an endocrine disrupting chemical. So we're exposed to these all the time. Why is it famous? It's famous because of baby bottles. So bisphenol A is an endocrine disrupting chemical. I have already told you all of the risks of working with endocrine disrupting chemicals. So why on earth would you make a baby bottle from something that contains an endocrine disruptor? Because you're then dosing a baby, the most sensitive age for humans. The reason we use plasticizers is to get them to the shape that we want. So there are technical reasons why you need to use plasticizers. Do we have to use BPA? Could we use something else? Well, BPA is actually pretty good. We know quite a lot about it. And this is a really interesting example where actually consumer preference led the way. So you might see in the top corner of this advert, BPA and BPS free. Companies were removing BPA and a related compound BPS from baby bottles before they were told they had to, because it became a marketing thing. They could say, buy our baby bottles, they are safer
We
than
don't have a drink or
X's baby
something, so we've
bottles.
got to the house and so we've got to the library or something.
So why do you have BPA in there, and what's the risk, particularly with baby bottles? Beyond the fact that young children are very sensitive, we also have the risk that when you make a baby's milk, you put it in a bottle, you shake it up, then you warm it up. And when you warm up something, you actually make it easier for the chemicals to come out of the plastic and into the milk.
To the toilet.
That's why we say for things like cling film as well, you shouldn't heat up cling film, because that helps the chemicals come out the cling film and into the food stuff you're covering. So this is why companies stopped using BPA in babies' bottles. They found an alternative plasticizer.
Pop in the
So why
house
don't we
and
just do that for everybody and for everything? The problem is BPA is critical for producing a vast range of medical devices, whether it's the catheter itself that's put in your arm, dialysis machinery, flexible tubing. BPA is fundamental to actually meaning that we can make medical devices that deliver the life-saving drugs that you need. So we can't stop using BPA. There isn't another alternative that we think is any safer. So we have to have BPA in medical devices, but this is where the challenge comes. So definitely no in baby bottles, definitely yes in medical devices. What about baked beans? So anybody who go home tonight, here's your experiment for the evening. Open up a tin of baked beans, actually pretty much any tin, and you'll notice it's got a plastic covering on the inside of the tin. That's there to help stop your food product being tainted by the tin. That contains an endocrine disruptor, plasticizer. It probably doesn't contain BPA anymore, but it did for decades. There are lots of places you're exposed to BPA that you will never know. And we just can't remove all of them because it is such a good chemical. So how do we learn to live with the risk? And this is where toxicologists come in. So the European Food Safety Authority is the European body that sets the limit of exposure to chemicals for what is safe. Back in 2015, they looked at BPA and they said, well, what's the safe limit? And they did lots of research and they came up with what we call a TDI, a tolerable daily intake. How much can you be exposed to this chemical and the risk to you be very small? And they came up with a number, 4 micrograms per kilogram of body weight. That number means nothing to you, but what is really important is somebody's worked that out, and then I can actually go and say, where are all the sources of BPA you were exposed to? I can add them all up, and I can go, is it bigger than that number? And if it is, we have a problem. If it's less than that number, then actually we're pretty safe. The risk is acceptable. So that was done, and we have now a limit, and we can regulate the use of BPA in a way where we can use the benefits of it and not worry about the risks. And I put in this second paragraph because it's quite useful, because it says it's used in a whole range of things, from bottles, tableware, storage containers, but it is prohibited in coatings and varnishes applied to food contact materials intended for infants and young children. So it is banned from use in baby bottles now because we don't think the risk is acceptable. So that's an example where toxicology was allowed to give us comfort. I'm going to finish my talk by talking about some work that we've been doing recently. So I've just come to the end of a European Union project looking at the impact of endocrine disrupting chemicals on the liver. So if you remember when I talked about the plasticizer in cling film, I said what it can do is it can take your healthy liver and it can cause fat to be stored in your liver. That causes scarring. That's fibrosis because of the damage it causes. If you have so much scarring, then you end up in cirrhosis, which is a really badly damaged liver. You normally need a liver transplant at that point. And then that progresses either to fulminant liver failure, your liver just stops working, or to liver cancer, neither of which have a particularly good outlook. So how do we understand the risk of moving down that pathway and try and protect? So this was a 5-year program, 13 million euros, something like that. But actually it was part of a multi-program cluster called Eurion, which was 50 million euros invested by the European Union to solve the problem of endocrine disruptors. Spoiler, we didn't, but I'll explain why. So far I've talked about you being exposed to one chemical at a time. But I've already told you endocrine disrupting chemicals are everywhere. So you're never exposed to one chemical at a time. You're always exposed to multiple chemicals. So what does that mean? Does that make it safer? Does it make it more dangerous? We don't know. So we were looking at chemical soups. What happens when you're exposed to multiple chemicals at once? So just to give you an example, lots of different chemicals here. Each of those chemicals will interact with particular receptors in your body and start them off doing something, responding to that exposure. But each of these chemicals can bind to multiple receptors. Each of these receptors will switch on multiple genes and start different response systems. So we have lots of different interactions going on. Does that happen with endocrine disruptors? So this is a piece of work done by one of my collaborators in Germany, in Tübingen. And what we've done is, here's a list of nuclear receptors. These are, if you like, the signaling parts of your body. They capture a signal and decide what to do with it, how your body's going to respond. Across here, we've got a whole range of endocrine disruptors. They're numbered, so you don't worry what they are, but I have highlighted, here's DEHP, my one from cling film, here's BPA, my one from baby's bottles. Anywhere where you see a colored in box, it means this chemical can activate that receptor. And I think you can all see that for each of these chemicals, they activate multiple different receptors. So it's not a simple, I touch here, I get a response down here. There's a whole network going on. What does that actually mean? What is the outcome that comes? And this is where my sort of research area comes in. I build computational models. I make digital models of the liver, and then I can start to play around. I can run scenarios. I can say, if I delete this system, does it change what happens? If I add in multiple exposures, does it change what happens? So we build models of the liver. Here, just to explain, here's an output of a simulation that we do. Effectively, if you've got a deep blue color, that means your liver is making very low levels of lipid, that first driver towards liver failure, liver cancer. If it's up in the yellows and the reds, it's producing lots of it. That's the danger sign. And what we can see is for each of these nuclear receptors, for lots of them, if you activate them, pretty much nothing happens as far as lipid metabolism is concerned, as far as driving towards that adverse outcome, that risk of metabolic syndrome. But if I activate AR, the androgen receptor, the more I activate it, the more I'm exposed to chemicals that activate it, the higher the risk of getting a fatty liver, diabetes, cardiovascular disease, liver failure, etc. is. There's another one called PPR alpha. The more I activate that, the more it drives towards a phenotype. That's for a normal, healthy person with low levels of fat, nice, young, healthy teenager. If you get to be a deputy vice chancellor, where you spend a lot of time sitting around, you probably have a little bit more middle-age spread than you would like. You have more circulating fat than you would like. This is what it looks like. I already start off with a baseline of quite a lot of fat in my liver. When I activate these receptors, something different happens. Now, activating this receptor, LXR, actually reduces the level of fat being produced. It's protecting the body from that fat. Really strangely, PPAR alpha, under low lipid, activating it drove towards fat. Under high lipid, activating it protects against fat. So different backgrounds have different effects. Just to make it worse, I've just told you, you never activate one receptor. You now have one chemical that hits one thing. So what happens if I activate multiples? This is what would happen, what I expect to happen if I activate multiple receptors at once, 3 different receptors. You don't need to look at the figure as such, just look at the pattern. This is actually what we see. It's completely different. So we see a change in when we progress from the oranges to the blues, and we have this really weird yellow piece in the middle. I still don't know what that means. But that shows when you activate multiple receptors, you get a completely different response than if you just activate one at a time. That starts to concern me because as a toxicologist, I know something hinky is going on. I don't quite understand why. And how do I help protect you if I don't understand what's going on? And this is why, as data comes through, we look at new data and we come up with new assessments. So, as I said previously, in 2015, EFSA came up with this tolerable daily intake for BPA. In 2023, they looked at it again, and they reduced the TDA from 4 micrograms per kilo to 0.2 nanograms per kilo of body weight. That's 20,000 times lower. That should mean that the level you can be exposed to is far lower. You should therefore be much safer. European politics being European politics, the Germans didn't quite agree with that. And the German Toxicological Institute, BFR, actually came up with a value of 0.2. So 20-fold lower than the original one, but not 1,000 times lower. The British committee that I've been part of for a number of years, the Committee on Toxicity, also looked at it, and we agreed with the Germans. And we now have in this country a new level of 0.2 micrograms per kilo body weight per day. But we set a level that says, I can look and go, if when I add all the sources together, you're below that, I can be confident you will be safe. So to bring this all together, I'm going to try in one slide cover about 500 years of history. I'm going to start with Paracelsus. So Paracelsus is the father of toxicology. He was, as it says on this beautiful picture, a famoso doctor. And he came up with a phrase, all things are poison and nothing is without poison. Only the dose permits something not to be poisonous. And I think what I've shown you tonight is essentially 500 years ago, he had it bang on the money because the endocrine disrupting chemical in cling film is a poison. At a high enough concentration, it will give you liver cancer. But at the levels you are exposed to it, normally, it's completely safe. Water, you don't drink it, you will die. If I drop you in the middle of the Atlantic Ocean, you will drown. So it is very much around the level of exposure. So what have we actually achieved in 500 years of toxicology? We've made it more complex. So we now have computational testing. We have in vitro testing. We have testing in animal systems. We have clinical trials in humans. And we have population studies where we look at what happens to people exposed naturally to chemicals in the environment. All of those experiments feed into the regulations that I've talked about. And the data that we get cycles around and feeds into the next lot of testing. So we still know that everything is a poison and it's only the dose, but now the uncertainty has got less. So I can be more precise in saying the level you're exposed to is concerning, or the level you're exposed to is not exposing, is not risky. So that's what toxicology has achieved, hopefully, in the last 500 years, is it should give you confidence that somewhere, somebody is calculating the risk of exposure to DEHP for a 6-year-old child wearing Crocs in Denmark. So you don't have to worry about it. And with that, I will finish. Thank you all very much indeed. First to say.
First, just to say thank you very much, Nick, for fascinating talk. Take us into places certainly I have never been or expected to go. But at least I now know I can continue to wrap my sandwiches in cling film, provided I don't stick them in the microwave immediately afterwards. But thank you for that very much indeed. We do have a few minutes for questions. If anyone has any questions they want to raise either here or in the on Zoom. Yes.
Yes, let me I'll repeat the question, which is, given that I've talked a lot about risk perception, what is Donald Trump's nominee for the health department going to think of toxicology? I think he's going to think of it what he wants to make of it. It is noticeable that a number of the picks for the president-elect have very firm views, sometimes not always fully rooted in fact. And the challenge is simple. We, as a group of individuals, have a responsibility to continue to communicate the work that we do. So one of the joys of my role sitting on committees is I meet pressure groups. I meet people from, I didn't talk about cabin air fume events this time, but cabin air fume events, I met the Airline Pilots Association. They were the politest, most intelligent pressure group I've ever met. I've also met a man who told me that the methanol in aspartame is different from the methanol in tomato juice and was unreasonable to the basics of chemistry. And you have to listen to all of them, and then you have to respond in a reasonable way. So yes, there are always concerns, and the answer is you don't throw your hands up, you keep on bashing and pointing out where the holes are and trying to reassure people where you can.
Any more questions?
One on
Eric.
So it's a really good question by Eric, channeling his inner Donald Rumsfeld. I've talked about chemicals I know about. I've talked about chemicals I can measure. What about chemicals that I don't know are in something? Chemicals that I can't understand yet. And I think that's actually where the endocrine disrupting chemicals are a good example. There's 700 of them. I don't know the level of every single one of them in your bottle of water. But what I can do is I can say, well, I know what will happen to one of them, and they're actually quite similar in their chemical structure, in their behaviors. So if I know what one of them does, I can tell what all of the ones in your bottle are likely to do. So I can do an equivalence type approach. And that's often what we do. We build on the thing that we're sure of, and we say, well, we'll throw in, so classically, you throw in 100-fold safety factor. You go, this is what I know. So I'll say, if I think that this is the point where above that concentration, it starts to get toxic, to make the safety factor, what I will allow you to be exposed with, I'll go 100-fold lower, because that gives us a little bit of breathing space. There's one online if you want. So there was one question which was, if we had to ban one chemical or restrict one chemical more, what chemical would it be? Well, I've already said I am extremely anti-smoking. I'm not going to pick tobacco, because tobacco, I'm going to use as an example. Cigarettes are fantastic because they contain procarcinogens, chemicals that can be turned into things that give you cancer. They also contain chemicals that induce the enzymes in your body that help turn those pre-cancerous chemicals into cancer-causing chemicals. And they contain something that's addictive. So when you have a cigarette, you want another one. So they are, if you like, the perfect storm of how to make somebody ill. If you smoke, then it is a 2/3 chance you will die of a smoking-related disease. We know this. So I'm not going to say it. Sugar is the one I'm going to pick, because actually the biggest crisis facing the world today is obesity. We know the solution: eat fewer calories, exercise more for most people. It's not quite that clear-cut, but it generally is. And the way that we use sugar in everything is a real problem. When you start to look at the risk of the chemicals I've talked about today versus the risk of some of the chemicals you know, tobacco, sugar, alcohol, all the ones I've talked about today are orders of magnitude less risky to you in everyday life. But we worry about them far more than we do the fact that I'm on my 15 Krispy Kreme donut of the day.
Any last questions?
Yes, is the very, very simple answer. So going back to my Daily Mail, what the Daily Mail does really well is it takes an absolute grain of truth and it spins it again and again and again and again until it becomes a really exciting story. In doing so, it forgets to think about actually the chance of it coming to reality. And that's where probability comes in. This is the risk. So the probability of getting a cancer, a smoking-related disease and dying of it is about 60% if you smoke. The probability of doing it if you're a passive smoker is less, but there's still one. You can start to think about distributions. You can think about distributions across ages, sensitive types. But it starts getting complicated. And as somebody who's taught undergraduate students for years, you use the word maths and they just often just stop thinking. It's so important. Yeah. Thank you. Thank you. And I think that's really kind of you. But it's what we all have to do. This is our collective responsibility. I have done many things like this. I have stood up and done comedy about this, because the more we learn to communicate with everybody, the easier it is to get those conversations over. Going back to scientists can be really boring. I can say that I am one. If you talk in a really boring, really accurate fashion, people switch off. You have to work out how you can get people to listen. There's one final question if you want. Sure. So they're related questions, which is, do you think we should remove PCB, so polychloride biphenyls, in the UK? And can we remove microplastics? Both of those are pollutants. Both of those have risks to long-term health. Would I love to see them removed? Yes. Do I think there's a practicable way of doing it, both in terms of physically achieving it and the cost it would be? Sadly, no. The horse has bolted. The challenge is now, how do we reduce that risk? So going to PCBs, dioxins, etc. What we do now is we monitor. So you do still get dioxins, quite high levels in tuna. So we actually monitor tuna before it goes on sale to make sure you're not exposed to it. So I think we're actually now in a limitation phase. We have to stop the production of these chemicals. That's why dioxins were banned. But microplastics, we have to think of other technologies, other ways of doing this, more biodegradable, so that they don't become a problem for our children, our children's children.
Right, I'm going to call a halt there and say again, thank you, Nick, for proving that you were not a boring scientist, but actually a fascinating speaker about this interesting and dangerous but important subject, and the importance of understanding the risk that some things really it's not worth worrying ourselves too much about. I shall go home reassured about that. Thank you very much indeed.